We're now going to look at the second method that we have to represent systems, which is signal flow graphs. So remember, previously we had said typically signal flow graphs are going to be used for state space analysis, whereas our block diagrams are used for frequency domain analysis. However, we can use either technique in either domain. So again, signal flow graphs are just providing us an alternative to using block diagrams. So for some of you, signal flow might be easier. For some of you, block diagram might be easier. In most cases, you can choose whichever one you want. So the difference between our signal flow graph and our block diagram is that in our signal flow graph, our systems are represented by branches. Whereas in our block diagram, of course, we had our blocks that represented our systems. So for example, a system would look something like this, a branch connecting various points in our overall system. The signals in a signal flow graph are just given by nodes. So signals are equivalent to nodes, whereas in our block diagram, remember our signals were the connecting branches between the blocks. So our signals are just going to be nodes here. So for instance, maybe this is some signal V of S. And so a couple other notable differences is wherever we have a signal, it's basically just going to be the sum of all of the signals flowing into it, or all of the systems flowing into it. So each signal is the sum of all signals. So these signals might be passing through a system, which we're going to see here in a second, but all signals flowing into it. And then another important thing to note is that we don't have any summing junctions. So no summing junctions in our signal flow analysis. And so what that means is that if we want to subtract something, then we have to have a negative sign associated with signals. So negative sign, with the systems. So negative sign is associated with our systems for subtracting. So if we have several inputs going into one place and we want to subtract one, we have to have a negative sign on our system. So an example to kind of show us these ideas is shown here. So a very simple overall system. We notice we have our signals, input signals R1 and R2, so these would be like two input signals. We also have an output signal C of S, and then some intermediate signal V of S here. In addition to these signals, we also have systems. So these are our subsystems, which we're going to talk about later how to combine to make one single system. We have a system G1, a system negative G2, and a system G3. So note that this negative sign is associated with this system G3 because again, we don't have any summing junction as we're combining the signals at V of S. So I've noticed I'm missing a parentheses there. So we don't have any summing junction, so that's why we have to have that negative with our G2. So if we wanted to write an expression for this system, we could say V of S is equal to R1, so R1 of S times G1 of S minus R2 of S times G2 of S. So anything that comes into this point, we're just going to sum it. All right, and then of course, going from V to C is pretty straightforward. We can just say our C of S is equal to V of S times G3 of S. And of course, we have some ways that we can sort of convert back and forth between signal flow and block diagrams. So that's what we're going to look at in the next video. And then after that, we're going to start looking at Mason's rule, which is the technique on how we can reduce a system to one single system so we can know sort of the one transfer function for our system.